The simplest of the hydrocarbon families, and the least complex of them, is a family of hydrocarbons known as the alkanes. The characteristic that sets the alkanes apart from other hydrocarbon families is the fact that all of the carbon-carbon bonds within these structures are single bonds, as opposed to double bonds or triple bonds. Now, as we lengthen the carbon chains, the difference between one member of the alkane family to the next is the addition of a specific structural unit, and that structural unit is a CH2 unit. Remember that carbon is tetravalent, which means that each carbon needs to form a total of 4 bonds. 2 of those bonds, as we lengthen a chain from the interior, we add carbons to the middle of the chain. Each carbon that we add is going to bond to the 2 adjacent carbons, hence the dashed lines that you see in the structure on the screen at present. That takes care of 2 of carbon's 4 bonds. The other 2 are filled in with hydrogens, hence the reason that the formula for this specific structural unit is CH2. Anytime you have a series of compounds where the structures differ from each other by a specific structural unit, such as CH2 for the alkanes, that's known as a homologous series. So the alkanes are a homologous series, and the homologue is the unit that they differ by. So the homologue for the alkanes would be CH2. Now, because there is such regularity to the alkane structures, we can put a mathematical formula to the molecular formula of the alkanes, and that general formula is CnH2n plus 2, where n equals the number of carbons found in the molecule. So for instance, if we had a 5-carbon alkane, the formula would be C5H12. 2 times 5 is 10, plus 2 is 12. If we had an 8-carbon hydrocarbon, 8-carbon alkane, the formula would be C8H18. If we had a 25-carbon alkane, we could actually draw it out and count all the hydrogens, but we could get there much more quickly if we simply used the general formula, and found that the molecular formula for a 25-carbon alkane would be C25H52. 2 times 25 plus 2. The reason that you have the plus 2 is because those end carbons at either end of the chain, they don't have a bond forming to another carbon on the other side. And so basically you have to plug the end of the carbon chain up, and that's where that extra hydrogen comes in. Hence the reason you have plus 2 in the formula. As far as where alkanes come from, most of them come from fossil fuels, be it natural gas, crude oil, sometimes coal. When crude oil is recovered from the ground, that crude oil is a mixture of many different sized hydrocarbons, alkanes, and even other families of organic compounds. That crude oil petroleum goes through a process known as fractional distillation, in which that crude oil mixture is heated, its components are vaporized, and they travel up through a large tower where the temperature gradually gets cooler, and as it passes the boiling point of the different fractions, they begin to condense out, and those purified fractions can be piped off into separate containers. The differences in the molecular weights determine what the boiling point is going to be that the individual components will condense out at. Alkanes themselves are also sometimes referred to as paraffins, and because they only consist of single bonds, they don't really react very readily with many other chemicals, not like compounds that have double bonds or triple bonds. Another nice thing about having these homologous series, of which the alkanes are a member of, or a type of, is that you get regularity in terms of the properties, chemical properties, and also physical properties. And they change in a fairly regular manner as the molecules get larger. For instance, you talk about boiling point. For your smallest alkanes, they'll only consist of 1 or 2 or 3 carbons. Those are typically gases at room temperature because they have such a low boiling point. Whereas when you start getting into hydrocarbon chains from 5 to 8 or 9, then they start to be more liquids. and then your larger hydrocarbons end up being your solids. And so the more carbons there are in the structure, the heavier it is, the more energy it would take to cause those molecules to change to a more chaotic state. And so we see that general trend, and not just with boiling point or melting point, but you can also sometimes see it with density, with chemical reactivity. When we name alkanes, and really the key to understanding organic nomenclature in general is to realize that each part of the name tells you a different part of the structure. Now with the alkanes, it's a very simple structure, and so there's only two main parts that we need to worry about. The first part is the stem, and sometimes you'll hear me refer to it as the prefix, but the stem or the prefix of the name is going to tell you how many carbons are present in that structure. The ending of the name gives you a clue as to what kind of bonding is present, whether it's single bonding, double bonding, or triple bonding. And seeing as how we're talking about the alkanes, we've already said that the alkanes consist only of single bond. So the first part of the alkane's name is going to tell you how many carbons are present. Now as far as these prefixes go, from 5 on up, they're the same as the prefixes that we used when naming molecular compounds: pent, hex, hept, oct, non, and dec. The first 4 are different from what we usually think of for prefixes indicating those numbers. Things like mono, di or bi, tri, tetra or quad for 4. For hydrocarbon naming and in organic nomenclature, the prefixes that are used are meth for 1 carbon, eth for 2 carbons, prop for 3 carbons, and bute for 4 carbons. So it goes meth, eth, prop, bute, pent, hex, hept, oct, non, and dec. And if we're talking about alkanes, where there's only single bonding present, the ending of all alkane family members' names is ane. So it's very easy to remember. Alkanes end with ane. And right now that might not seem like a big issue, but when we get into some of the other families, the alkenes and the alkynes, you'll see how that ending indicates the difference in those structures in terms of the bonding that takes place. So if you take, for example, a 3-carbon alkane, a 3-carbon chain where they're all linked together with single bonds, you would name that propane. Prop for 3 carbons, ane to indicate that there's only single bonding present. A 10-carbon chain would be known as decane. Dec for 10 carbons, ane to indicate all single bonds taking place.